black holes, the key to understanding the universe. Extended alternative script, 2,000 words. Imagine an object with gravity so overwhelming that nothing, not a spacecraft, not a beam of light, not even time itself in the way we understand it, can escape its pull once it gets too close. That single idea, almost absurdly simple on the surface, has turned into one of the richest and strangest problems in all of physics. That object is a black hole, and this script is a journey through why so many physicists now believe that black holes aren't just cosmic oddities. They might be the single best clue we have toward understanding the true nature of reality itself. To get there, we have to walk through several ideas: escape velocity, the event horizon, the singularity, Hawking radiation, the information paradox, and finally, the strange modern idea that space and time themselves might not be the bedrock of the universe at all. Each step builds on the last, so let's take them one at a time. 1. The idea of escape velocity. Long before anyone had the mathematics to properly describe a black hole, the basic intuition behind one had already been imagined. The story begins in the late 18th century, in the 1780s and 1790s, with two thinkers working independently of each other, unaware that they were converging on the same extraordinary idea. One was John Michel, an English clergyman and natural philosopher with a deep interest in astronomy and gravity. The other was Pierre-Simon Laplace, the great French mathematician whose work would later become foundational to celestial mechanics. Neither had access to anything like modern physics, yet both arrived at a strikingly similar thought experiment built around a concept called escape velocity. Escape velocity is simply the speed an object needs to completely break free of a gravitational field, never to fall back. For Earth, that speed is about 11 kilometers per second, roughly 25,000 miles per hour. Leave the surface slower than that, and gravity eventually pulls you back down. Leave it faster, and you sail off into space, never to return unless you choose to. Now scale that idea up. The more massive an object, and the more tightly its mass is packed together, the stronger its surface gravity, and the higher its escape velocity. The Sun, far more massive than Earth, has an escape velocity of around 600 kilometers per second. Michel and Laplace pushed the thought experiment further. What if you kept adding mass, packing it tighter and tighter? At some point, they reasoned, the escape velocity required to leave the surface of an incredibly dense, massive object would exceed the speed of light itself. If that happened, light emitted from the surface would never be able to leave. The object would be, in a very real sense, invisible, a dark star, to use the language of the time. Michel even attempted rough calculations suggesting how large and dense such an object would need to be. It's a beautifully simple idea, built centuries before Einstein, general relativity or quantum mechanics existed, and it planted a conceptual seed for everything that followed. 2. The event horizon, where time seems to stop. Fast forward more than a century past Einstein's 1915 theory of general relativity, and the crude 18th century notion of a dark star evolved into something far more precise and far stranger. The black hole, and specifically the idea of the event horizon. Picture a black hole from the outside. Surrounding it is an invisible boundary in space called the event horizon. This isn't a physical surface like the crust of a planet. It's a mathematical boundary, a point of no return. Cross it, and no matter how powerful your engines are, no matter if you could theoretically travel at the speed of light, you cannot escape the gravitational pull of everything inside. What makes the event horizon so conceptually strange isn't just that nothing escapes, it's what general relativity predicts happens to time there. From the perspective of someone watching from a safe distance, an object falling toward a black hole appears to slow down as it nears the horizon, its light stretching and dimming, seemingly frozen at the boundary forever. In a real sense, the event horizon is a place where, from an external vantage point, time appears to stop entirely. This single feature, a boundary where our normal intuitions about space and time break down, is what makes black holes such a powerful laboratory for physicists. Unlike the singularity at the centre, which we'll get to next, the event horizon is a place where we still believe general relativity's equations hold up. It's calm, mathematically well-behaved geometry. And yet, as we'll see, even this calm region turned out to hide a deep and unresolved problem. 3. The singularity, not a place but a moment in time. So what's actually inside a black hole? The popular image, the one most people picture, is of an infinitely dense point at the very centre. A singularity where all the collapsed matter of a dead star has been crushed down to a single dimensionless location. But this picture, while a useful shorthand, isn't quite right, and understanding why requires a small conceptual leap. If you look at the mathematics of general relativity applied to a black hole, visualised elegantly through what's called a Penrose diagram named after physicist and mathematician Roger Penrose, you find something genuinely strange. Inside the event horizon, the roles of space and time effectively swap. What we'd normally think of as directions in space become directions in time, and vice versa. The consequence is bizarre but important. The singularity isn't really a location you could point to and say, there it is. It's better described as a moment, specifically the final moment of time for anything that falls in. Just as you cannot avoid tomorrow once today has passed, anything crossing the event horizon cannot avoid reaching the singularity. It is, in effect, the future, not a place in space at all. For decades, physicists largely treated the singularity as an unsolvable mystery, a place where our equations simply break down and give nonsensical answers. Infinite density, infinite curvature. Many assumed this problem would remain unsolved for a century or more, a dead end walled off from the rest of physics. What changed everything wasn't a fresh assault on the singularity itself, but a shift in attention toward the seemingly calmer, better understood region, the event horizon. 4. Hawking's revolution. In the early 1970s, Stephen Hawking made a discovery that would reshape black hole physics entirely, applying the principles of quantum theory to the region right at the event horizon. Rather than the impossibly extreme conditions at the singularity, Hawking found something nobody expected. Black holes are not perfectly black after all. According to quantum mechanics, empty space is never truly empty. It's filled with pairs of virtual particles that flicker in and out of existence constantly, an effect predicted by quantum field theory. Near the event horizon of a black hole, something unusual can happen to these particle pairs. One partner might fall across the horizon into the black hole, while the other escapes outward into the universe. When that happens, the escaping particle carries away real energy, energy that ultimately comes from the black hole's own mass. This steady trickle of particles is what's now called Hawking radiation. It means black holes are gradually losing energy and mass over time. Slowly, imperceptibly, they are evaporating. Given enough time, an almost unimaginable span, far longer than the current age of the universe for most black holes, they would shrink and eventually disappear entirely. This was a profound shift in how physicists thought about black holes. They were no longer eternal, changeless prisons that swallowed matter and energy forever. They had a lifespan. They had a fate. And crucially, this discovery also opened a Pandora's box of a question that physics is still grappling with today. 5. The information paradox. If a black hole eventually evaporates completely, leaving behind nothing but a diffuse cloud of Hawking radiation, what happened to everything that fell into it over its lifetime? All the matter, all the structure, all the detailed information about every atom that was ever swallowed, where did it go? This question strikes at one of the deepest principles in physics, the conservation of information. In essentially every other area of physics we understand, information is never truly destroyed, even when it looks like it. Take a book and burn it to ash. From an everyday standpoint, the information in that book, the words, the story, seems gone forever. But in principle, if you could capture every photon of light, every particle of smoke, every scrap of ash produced by the fire, the complete information about that book would still be encoded somewhere in that collected debris. Nothing was truly erased. It was just scrambled and redistributed. Black holes appeared to violate this principle catastrophically. If Hawking radiation is produced by quantum fluctuations right at the horizon, seemingly independent of whatever specific matter fell in long ago, then the radiation streaming out of a black hole would carry no information at all about what was originally consumed. When the black hole finally evaporated completely, all of that information, the specific details of every star, planet or spacecraft that ever fell in, would simply cease to exist. This became known as the black hole information paradox, and for decades it stood as one of the most significant unresolved conflicts between quantum mechanics and general relativity, the resolution still being actively worked out today through ongoing research seems to lean strongly toward information not being lost after all. Recent theoretical work involving complex tools like quantum entanglement calculations and something called entanglement wedges suggests that the information about everything that fell into a black hole is in fact subtly encoded within the correlations of the Hawking radiation itself. In principle, if you could collect every particle of radiation emitted over a black hole's entire lifetime and feed it into a sufficiently powerful quantum computer, you could reconstruct everything that ever fell in. The universe, it seems, really does conserve information, even when confronted with the most extreme gravitational environment imaginable. 6. Space and time may not be fundamental. This is where the story takes its most radical turn. The methods physicists developed to resolve the information paradox pointed towards something far stranger than anyone initially expected. The possibility that space and time themselves are not the fundamental building blocks of reality, but rather emergent phenomena arising from something deeper and more basic. The leading idea here falls under the umbrella of emergent space-time. The core suggestion is that the fabric of space and time we experience, the 3 dimensions we move through, and the 1 dimension of time we experience passing, might arise from an underlying structure made of quantum entanglement between more fundamental components. We don't yet know exactly what those more basic components are, but the mathematics connecting black hole entropy, quantum information, and the geometry of space-time keeps pointing toward this conclusion from multiple independent directions. If this idea holds up, it would mean that black holes are far more than just extreme astrophysical objects. Dead stars collapsed under their own gravity. They become natural laboratories, the only objects we can actually observe in nature that push our theories to their absolute breaking point, forcing us to ask sharper and more precise questions about what space, time, and reality fundamentally are. This also has enormous implications for some of the biggest unanswered questions in cosmology, including whether the universe itself had a true beginning in time. It's difficult, maybe even impossible, to properly answer a question like, did time have a beginning? Without first understanding what time actually is at its most basic level. Black holes, strange and violent as they are, might be exactly the kind of natural experiment the universe has handed us to help answer that question. Closing thought. Einstein once said that if you look at nature carefully enough and keep pulling at the intellectual threads, refusing to stop even when the picture gets uncomfortable or strange, you can sometimes catch a glimpse of something deeply hidden, some deeper structure underlying all of reality. Black holes may be exactly that glimpse. They sit at the crossroads of gravity and quantum mechanics, of geometry and information, of space and time. Nobody yet knows exactly where this research will ultimately lead or what the final theory of quantum gravity will actually look like. But few areas of modern physics offer such a tantalizing hint that something profound, something currently hidden just beneath the surface of our best theories, is waiting to be understood.